Hello and welcome to another Common Core Geometry lesson by eMathInstruction. Today we're going to be doing Unit number 9, Lesson number 3 on more work with inscribed angles. So the last lesson was all about inscribed angles and learning sort of what the definition of an inscribed angle was and how to recognize it, and also some important properties of inscribed angles. And what we're going to do today is we're going to start by reviewing those important properties, doing one exercise that at least kind of refreshes the ideas that we saw in the last lesson and in the last homework, and then we're going to extend and look at more things having to do with inscribed angles. They're very important in circle geometry. So let's get right to it. All right, inscribed angles. Angles whose vertex is on the triangle and whose rays both intersect the circle, right? Simple enough. I've got a circle, I've got a vertex of an angle on a circle, the two rays intersect the circle. That's an inscribed angle, angle ACB or angle BCA. Now, there are some very, very important facts about inscribed circles. The first one, the one that we really dedicated a lot of time to in the first lesson on inscribed angles, was that their measure is always 1/2 the measure of their intercepted arc. In other words, measure of angle C, or ACB, is 1/2 the measure of arc AB. All right? Always. Okay, and keep in mind, of course, that the measure of arc AB is equivalent to the measure of, the central angle AOB that it intersects it. All right, another important fact that we saw in the last lesson. Inscribed angles that intercept the same arc have the same measure. So in other words, angle ACB and angle BDA both intercept arc AB, and therefore they must have the same measure. Right? They're both half of arc AB, whatever arc AB is, and since they're both half of the same measurement, they themselves must be the same. Now, something that we saw in the last lesson's homework, but we didn't see in the last lesson proper, was the fact that whenever we have parallel chords, they intercept arcs that have the same measure. So if chord AB is parallel to chord CD, then arc BD and arc AC have the same measurement. Now you might say, well, wait a second, that doesn't have anything to do with inscribed angles. There's no inscribed angles there. Well, that's not actually entirely true. All right. In fact, we proved this on the last lesson, homework that is, by basically throwing that in and then saying, well, because they're parallel, those two angles must be equal. And if these two angles must be equal, given that they're both inscribed angles, then these arcs must be equal because these arcs would have to be twice the measure of those two alternate interior angles. So there. Even if you didn't have a chance to do the homework from that lesson, you now hopefully have a sense for it. It also just looks right. It looks right, right? If I've got these two parallel chords, that arc and this arc look like they should take up the same amount of the circle, if you will. All right, so let's now use a little bit of that. Let's take a look at exercise number 1. In circle E, AB is parallel to CD, and the measure of angle ADC is equal to 42 degrees, and the measure of CD is twice the measure of AB. Find the measure of arc AB, show your work. All right, great. So let's make sure that we know what we're trying to find, okay? So let me kind of highlight that in blue, okay? I'm looking for the measure of arc AB. This is what I want, okay? So what do I know? Well, I know ADC is 42 degrees. What can I do with that 42 degrees? What other thing can I learn? Well, one thing that I can figure out is I can figure out that the measure of arc AC, right, which is right here, right, the measure of arc AC would have to be twice that 42 degrees. So that's got to be 84 degrees. But then again, because these two chords are parallel, the measure of arc BD, well, that didn't work. The measure of arc BD must also be must also be 84 degrees. Okay? So I can actually kind of mark these things on my circle. 84 degrees, 84 degrees. What else do I know? Well, I've been told that the measure of arc CD has to be twice the measure of arc AB. So you know how to play this game. Let's let the measure of arc AB be equal to x, and the measure of arc CD equal 2x. Let's also have those labeled on our picture. So how can we solve for x? Because ultimately that's what we want, right? We want the measure of arc AB, so we need to solve for x. Well, if I add up all the arcs as I go around the circle, I must have a sum of 360 degrees. In other words, if I've got 84 plus 84 plus x plus 2x, that's all got to add up to 364 degrees. Or sorry, 360 degrees. Of course, the 84 plus the 84 will add up to 168 degrees. The x and the 2x will add up to 3x. All right, obviously now I can do just a little bit of algebra by subtracting 168 from both sides. All right, let's do that quickly on our calculator. 360 minus 168 will give me 192. Divide both sides by 3. And x, which is what I'm looking for, right? This dude divided by 3 is 64 degrees. All right, and that's it. That's the whole deal. And that actually uses numerous properties of inscribed angles that we already learned. It used the fact that that inscribed angle had to be half of the arc that it intercepts, or of course you could say it as that the arc that's intercepted must be twice the measure of the inscribed angle. It used the fact that two parallel chords intersect arcs that have the same measure, so if that's 84, that's 84. And then it used the fact that when we add up all the arcs that go around a circle, we must have 360 degrees. Simple enough. All right, take a moment, write down anything you need to, and then we'll move on and discover some more things that are important about inscribed angles. All right, let's move on. Another important property of inscribed angles, a very important property. Okay, so let's take a look at exercise number 2. In circle A, diameter BC has been drawn. Awesome. Explain why angle BEC, BFC, and BDC must all be congruent. Why do all three of those angles have to be congruent? Take a moment and try to write something down. All right, well, let's take a look. Let's just make sure. Let me kind of highlight. All right, BEC. That's that angle. BFC. That's that angle. And BDC. That's that angle. Well, this is great because they must equal, because they all intercept the same arc BC. Right? They all intercept arc BC. Letter B, what is their common measure? Explain. In other words, what would be the measure of that angle, and that angle, all of which have to be the same angle? It has to be 90 degrees. Okay, why is this? Well, it's because the measure of arc BC is equal to 180 degrees. It's neither really a major arc nor a minor arc, BC, right? It's halfway around the circle. Whether we're going this way or this way doesn't matter. And because the inscribed angles are always 1/2 of the intercepted arc, right? All those angles, like the measure of angle BEC, must be 1/2 of 180, so 90 degrees. And this is really cool. That's a 90-degree angle. That's a 90-degree angle. That's a 90-degree angle. And so what exactly is this property? This is the property that says that any angle, any inscribed angle, right, that intersects a half of a circle must be a 90-degree angle. All right? Another way of putting it is any triangle that is inscribed in a semicircle must be a right triangle. All right? Must be a right triangle if it's kind of got this configuration. And what that allows me to now do is it allows me to solve all sorts of right triangle problems. So take a look at letter C. It says if the radius of circle A has a length of 5 inches and BD is 6, then find the length of DC. All right, simple enough. Let's label some things. Okay, it says the radius of circle A has a length of 5 inches. All right, so that means this is 5 inches, means this is 5 inches. We know BD is 6 inches, and we want to know the length of DC, this. Well, ultimately what we have now is we have the following right triangle. Let me just move this up a bit. We have a right triangle that looks like the following. I'll even label all the vertices. B, C, D. BD is 6. BC now is 10, not 5. And I'm looking for DC. Maybe I'll call it A. And of course, for this, I can use the Pythagorean theorem, right? And I can say, well, whoops, that doesn't look like an A. I can say A squared plus 6 squared is equal to 10 squared. A squared plus 36 is equal to 100. A squared is equal to 64. A equals the square root of 64. So A is 8, right? Which is what I was looking for, DC. All right? This fact about inscribed angles is kind of easy. It comes directly from what we learned about the fact that an inscribed angle is 1/2 of the measure of its intercepted arc. But the thing about this particular property is the fact that it gives rise to these right triangles. And actually, let's kind of look at it in GeoGebra. Any inscribed angle that intercepts a semicircle must be a right angle. And this is cool. So here we've got this circle, right? And we've got the diameter BC drawn in, or BAC drawn in. And what we see here, right, is that no matter where I put angle D, whoops, right, no matter where I put this, let me try to make this circle a little bit smaller so it'll fit in here, that angle is a 90-degree angle, and then triangle CDB, or BDC, is a right triangle. And it's so cool, no matter where I put it, that is a 90-degree angle. All right, really kind of neat. I could do this all day. But you probably wouldn't want to watch the video then. All right, so let's keep going. Let's see another problem that involves this. In circle O shown, diameter AC has been drawn. If OC is 8 and AB is 5, find the measure of arc BC to the nearest degree. Wow, this is interesting. Pause the video and see if you can figure out how to do this problem. All right, this could be tricky for a number of people. Hopefully not, but let's take a look at what we know. Because AOC is a diameter, automatically that makes angle B a right angle and makes triangle ABC a right triangle. Now that means any kind of problem that we've ever asked about right triangles, we can now put in this problem. Such as in the last problem when we had the Pythagorean theorem. All right, but let's see what we're being asked now and what we're being told. OC is 8, so of course that's 8 and that's 8. AB is 5, so that's 5. And what I want is the measure of arc BC. Now, certainly one thing I can say after the last couple lessons is that the measure of arc BC is equal to twice the measure of angle A. Right? This inscribed angle A would have to be half of arc BC, and therefore arc BC would have to be twice the measure of angle A. So ultimately, if I can figure out the measure of angle A, I can double it to find the measure of arc BC. So let's actually extract that right triangle just for a moment. All right, because this is what we have now. We've got A, B, C. This is now 16, and this is 5. And if I can figure out the measure of angle A, I'm golden. But what will allow us to do that? What can we use, what should be in our toolbox right now that is used with right triangles if we have two sides of a right triangle that will allow us to find an angle? Well, it's going to be trig, right? Trigonometry. Trigonometry. The Pythagorean theorem could allow us to solve for side BC, but that wouldn't do much for us. What we need to use is trig. And of course, with trig, we've got SOHCAHTOA. We have to figure out which ratio to use. Well, that's all about the angle we're looking for. That's angle A, and 5 is the adjacent side. 16 is the hypotenuse, and so that is our cosine ratio. In fact, we can say that the cosine of angle A is 5/16. That will mean, or lead to, the fact that A is the inverse cosine. That almost was a -1, but not quite. The inverse cosine of 5/16. And now let's bust out of this program really quick and figure out what that is. Now remember, whenever you're doing trig on your graphing calculator, you want to make sure, as always, that you're in degree mode. But I am. Okay, I need the inverse cosine of 5/16, and that's 71.79, etc. So 71.79, let's say. So angle A is 71.79 degrees. Angle A is a pretty large angle. It seems reasonable. But now arc BC, right, which is actually what I'm looking for, must be twice the measure of angle A. So I'll just kind of pop over to my calculator right now, do ×2, and there's our arc. 143.58, so rounded to the nearest degree, 144. $144 degrees. Probably the hardest part of this problem, I'm going to just keep getting that pointer there. The hardest part of this problem is realizing that you have to use right triangle trig. All right? Nobody mentions a right triangle in this problem. You just have to simply know that angle B has to be a 90-degree angle because it's intercepting a 180-degree arc. Once you even know that this is a right triangle, then you have to realize, I've got a right triangle. I know two sides of the right triangle, the 5 and the 16, and I can use right triangle trigonometry, specifically the inverse trig ratios, or the inverse trig functions, sorry, in order to figure out the angle that I need. Then I double it to find the arc I need. There's a lot that goes into this problem, even though it's not a too terribly difficult problem. All right. Well, write down anything you need to, and then we'll move on. Okay, let's do it. Next problem, or the next thing that we're going to explore, has such a cool name. They're called Cyclic Quadrilaterals. Cyclic Quadrilaterals. A name that one might say is sick. I mean, it's really cool. And of course, you know what a quadrilateral is. A quadrilateral is a four-sided figure. You know, squares, rectangles, rhombuses, trapezoids, etc. A cyclic quadrilateral is any quadrilateral that has all four vertices on a circle. A, B, C, D here is a cyclic quadrilateral, right? Because all four of the vertices lie on a circle. Now, don't get me wrong. Not every quadrilateral can have its vertices on a circle, but you can certainly envision situations, right, where, you know, you just take a circle, you put 4 points on it. Well, that didn't work. You take 4 points on it. You connect them with straight line segments, and that's a cyclic quadrilateral. So what's important about cyclic quadrilaterals? Why would we even study them in today's lesson? Well, let's take a look at a cool property of them. So in this case, I've got a cyclic quadrilateral with all the angles labeled for you. And let me read through the problem. Exercise number 4. In the diagram of circle E shown, quadrilateral ABCD has been inscribed and its angles measured as shown. What is the relationship between opposite angles in this quadrilateral? All right, I'd like you to play around with the values of the opposite angles of this quadrilateral and see if there's some kind of relationship with them. This calculator should be a bit of a clue. Go ahead. All right, let's talk about them. Well, probably the most natural thing to do with the opposite angles is to add them together. So let me take that 117 and add it to its opposite angle. Let's see. 117 plus 63, 180. Well, that's kind of cool, right? Let's do the other one. 106 plus 74. Huh, 180. Also 180. And what you would find is that always works. Opposite angles in cyclic quadrilaterals are supplementary. They always add up to 180 degrees. Isn't that amazing? That's really kind of cool. I mean, now I might start to get a little confused in your head with things like parallelograms where adjacent angles are 180, all right? But not add up to 180, but not necessarily opposite angles. So, letter B. Explain why this relationship should always hold for cyclic quadrilaterals. I'd like you to think about that for a minute, okay? Just think about it, maybe even just use this diagram, but maybe not the degree measures shown in it, and think about why opposite angles in a cyclic quadrilateral should always add up to 180 degrees. All right, let's talk about it. Well, it's really cool. And again, don't worry so much about the exact angle values here, the 117, the 63, etc. But let's key in on angle A and angle C, right? Now I want you to think about this for a minute, right? Angle C intersects minor arc BD, and angle A intersects major arc BCD. BCD. Now think about that. So what we know automatically is that opposite angles opposite angles will intercept arcs with the same endpoints but one is major and one is minor. All right? Now think about that. That means that this angle, and likewise this angle and this angle, intercept two arcs whose sums must be 360 degrees, right? So we could even kind of prove it in this case. Forget about the 117 and the 63. We could literally say, well, arc AB, measure of arc AB, plus measure of arc CB must be 360 degrees, right? It's got to be, okay? But keep in mind, right, that the measure of arc AB will be twice the measure of angle C. The measure of arc ACB will be twice the measure of arc A, right? And if twice the measure of C plus twice the measure of A is 360, then I can just divide both sides of this equation by 2, and I find the measure of angle C plus the measure of angle A must be 180. At its essence, though, right? As its essence, we don't even need any kind of algebraic proof. Opposite angles in a cyclic quadrilateral will both intercept arcs that have the same endpoints and therefore add up to 360 degrees. But those are the arcs adding up to 360, right? The angles themselves will always be half of the arcs that are intercepted. So since the sum of the arcs intercepted is 360, half of that would have to be 80. This is a standard that is specified in the Common Core standards. The Common Core geometry standards state that students will know that opposite angles in a cyclic quadrilateral are supplementary, that they add up to 180 degrees, and they'll know why, right? And again, it all has to do with just keying in on A and C, right? That A intersects this arc, C intersects this arc. Those two arcs always will add up to 360, and because these two measures are going to be half of that, they have to add up to 180. All right, so let's apply that in one last problem, okay? So, exercise number 5. Quadrilateral QRST is inscribed in circle W as shown below. The measure of angle QRS is 12 degrees less than 3 times the measure of angle QTS. And measure of RQT is equal to measure of RST. Great, wonderful, good to know. Determine the measure of angle QTS. All right, so first things first, let's make sure that we understand what we're trying to find in angle A. We need to find the measure of angle QTS. QTS. Now again, what are we really told? Well, first thing is that the measure of QRS is 12 degrees less than 3 times the measure of QTS. So if I let the measure of angle QTS be x, then I will have to let the measure of angle QRS be 3x minus 12. Okay? But the key here now, this is 3x minus 12 and this is x, is that because this is a cyclic quadrilateral, that angle plus that angle has to be 180. And that's what, if you hadn't watched the last part of the video, you wouldn't know going into this problem. You would have no idea. But now we can just do 3x minus 12 plus x is 180. Right? That's 4x minus 12 is 180. Adding 12 to both sides, we'll get 4x is 192. Dividing by both sides by 4 and bringing our calculator into the mix, 192 divided by 4 equals, and that angle that I'm looking for is 48 degrees. All right? Now letter B says, what is the common measure of RQT and RST? Well, see if you can answer that problem. Go ahead. All right, last problem of the lesson. Well, we were told that RQT and RST are equal to each other. At least the measure of those angles are equal to each other. Well, I mean, maybe we'll call them Y. I don't want to call them X. I've already used X up. And again, because this is a cyclic quadrilateral, that measure and that measure have to add up to 180. So, well, Y plus Y is 180, which quite frankly means Y must be 90 degrees. Both of those are right angles. All right, let me step back, let you take a look, and then we'll wrap up. All right, let's do it. So today we saw 2 important facts that stem from inscribed angles. One of those facts is that when we inscribe an angle in a semicircle, that angle must be 90 degrees. And again, that's simple enough. An arc along a semicircle measures 180 degrees. An inscribed angle is always 1/2 the measure of the intercepted arc. So if we've got an inscribed angle that intercepts a 180 degree arc, it's got to be a 90 degree angle. Now the important thing about that is then any problem involving 90 degree angles, specifically the Pythagorean theorem in right triangles and trigonometry in right triangles, could come into play on this homework set. So watch for both of those. The other piece that we saw, right, was cyclic quadrilaterals, and the fact that a cyclic quadrilateral is a quadrilateral where all four vertices lie in the circle. And we learned the fact that the opposite angles in cyclic quadrilaterals must always add up to 180 degrees. All right. So in the next lesson, we're going to actually break away a little bit, thankfully, from inscribed angles, but we will see them a little bit. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.